Thank you. Thank you. All right, I'm the last speaker, and there are a lot of equations, okay? So it's fine. If you fall asleep, it's fine. If you start snoring, it's okay. Okay, so I'm going to be talking about implementing the Koopman-von Neumann approach in continuous variable quantum computing. Who has ever heard of Koopman-von Neumann formalism? This guy has, she has, he has. Not too many, including some of the physicists, right? Okay, and in fact, Frank Wilczek was just brought up. He's been interested in this. In fact, he just dropped like an educational video. He's a professor at multiple universities, so he was maybe teaching a course at MIT, but he was somewhere in another university, somewhere else in the world. But he was giving, and he has notes on the Koopman-von Neumann. Now, I'm going to try to do in less than 10 minutes what he did in an hour. So that's a tall order. But, so what's the motivation? This is dense. But don't worry, our goal is to simulate nonlinear dynamics. Like this is an x dot, a vector, equals some function, where the x's are just, it's nonlinear terms, okay? And this is like, so this is really, we're collaborating, this is a collaboration with Olivier and Zhenfeng. And Zhenfeng, we're gonna be really focusing on her kinds of nonlinear dynamics, like in fluids. But it also turns out that like mass action of molecular networks are solved like in biomedical engineering. I do that with my kind of computational biology hat on. And I'm not going to go through this whole list of challenges, but it can be, right, Zhenfeng, it can be numerically challenging. Or is it just easy? Are we wasting our time? No, it's pretty tough. That's all that's saying. And then what I'm going to just point out is that the Koopman-von Neumann formalism and photonic quantum computing are basically a match made in heaven. They really go together, and it could be a killer app. So basically, Koopman-von Neumann, as I'll show you, recasts nonlinear dynamics as unitary evolution on an infinite dimensional Hilbert space. Okay, that's a lot of words, blah, blah, blah. Okay, but a photonic quantum computer, you've kind of gotten a taste of it, is a continuous, has this Q mode, continuous variable mode, and it acts on functions. And so even the basis state representations are integrals, not sums, not discrete sums like we have shown you before. So people who have thought about already, well, God, infinite dimensions, 2 to the n, where n is like 100 qubits or something, that's big, but it's discrete, and that can still introduce errors in this framework, because the Koopman-von Neumann is really set up for infinite dimensional Hilbert spaces. So I'm just going to try to convince you that this is a natural thing, and I'm going to show you the nature of our collaboration. Okay, so what is Koopman-von Neumann? Okay, here's our goal. We're going to simulate x dot equals dx dt. It's some function, and this is nonlinear in x. And we're going to rethink, this looks like a velocity, we're going to define it as a velocity. Okay, for one of the first steps is you simply define the continuity equation. And all this is you're going to define a probability density, and you're just going to assume that it's conserved. It flows like an incompressible fluid. If you have a little volume and some density goes down, well, that same amount of density goes through surfaces. That's it going down in the volume, it's going through the surfaces. That's all that is. Okay, and then the way Koopman-von Neumann recasts the dynamics is that you evolve this probability density, and then you can calculate expectation values, averages, observables. And in particular, one of them is x itself. You calculate the observable of x, and that's going to kind of show you solve your evolutionary dynamics. Okay, are you with me? Everybody with me, more or less? Okay, now the first big step of Koopman-von Neumann, and we're going to go down the path of what you would do in developing a quantum theory. You define the probability density as psi star psi. Remember the Born rule? When you take this, this defines probabilities in quantum mechanics, and that's what we're going to apply. So we're just going to take this and just plug it into there. Okay, this is one of the prescriptions of quantum mechanics. All right, and I'm just going to say one thing. The formulation I'm going to show you is extremely general. So This could be a phenomenological equation. It could be like a fluid dynamics equation, or you could be modeling time series data with this, but it also includes Hamiltonian dynamics. Okay, and so the one thing I just want to point out that's weird, this is why I wrote this, is that just think of all, instead of normally you'll see Hamiltonian dynamics written in terms of Q's and P's, and all this is really Newton's evolution according to Newton's laws. But you can rewrite it all in terms of X's, and you'll see why I do that, hopefully, in a moment. Okay, so what's the next step? So what, and I'm deriving the whole Koopman-von Neumann formalism in front of you. So you shove that definition of the probability density of psi star psi into the continuity equation, and all you do is a little bit of vector algebra. That's it. And you end up with this, okay? This d psi dt equals this v dot the gradient plus a gradient dot v acting on psi. That kind of looks like a Schrodinger equation, doesn't it? You remember the Schrodinger equation that I showed you and some people are flashing it in front of you? It looks awful similar. Well, the next step in KVN is you now do exactly what you do in quantum mechanics. You take x to an operator, and you take minus h bar gradient, and that you assign to the momentum. But here's where, for people that are used to quantization of quantum mechanics, this includes some of the original momenta. If you were defining the system as a Hamiltonian evolution, I'm saying use all these x's. We're going to define a whole new set of p's. Okay? So just for the aficionados, the original momentum and position variables now commute in the Koopman-von Neumann language. That's just a little side detail. But don't get lost. This is like a Schrodinger-like equation that was easy to get to, and all we do is do exactly what we normally do in quantum mechanics and assign x to an operator and the gradient to a momentum operator, and these satisfy classic, this is classic commutation relations, okay? That just means xp operation is not equal to px. That's all that says. All right, so then what you arrive at when you make those substitutions, you arrive at a Schrodinger-like equation, which is the Koopman-von Neumann equation. And here's the Koopman-von Neumann Hamiltonian. I just substituted the del for p, and I put a hat on the x's. And in fact, this also satisfies another classic equation of motion in quantum mechanics. You can derive it from the xp commutation relation. dx dt is actually, this is just the Hamilton's equation of motion, and you get back consistently your original equation, which is very beautiful. That's your original starting formula. And you get it completely from now as a self-consistent result of quantizing theory. But remember what we're doing. We're turning a problem into a quantum mechanical-like problem to solve a classical evolution problem. At the end of the day, we're going to get the rho, the density from psi star psi, and calculate like the average of x and follow the evolution of a classical dynamical problem. Okay, but back to solving it in quantum land, this is exactly how you solve a quantum mechanical problem with a Hamiltonian and evolve it. But there's a challenge when, for example, let's say your HKVN is composed of two terms. Okay, what Olivier can do with us is he can evolve this Hamiltonian. This you can associate with a particular operation on an optical quantum computer, and this one. However, if your full Hamiltonian is this, the unfortunate reality, which you'll see is the case often and in our problem, is that H1 and H2, when they don't commute, this full Hamiltonian is not equal to this. So we don't know how to decompose the gates yet. For that, Olivier and others, and this is a very powerful central equation that's used in quantum computing, there's something known as the Trotter-Suzuki formula, where if you take itsy-bitsy time steps, but you take p of them, so the itsy-bitsy means you take your original time, how much you want to evolve in time, divide it by p, and then do that p times, you can now implement each individual optical gate. Okay, any questions about that? This is the Trotterization. So now it's implementable. Okay, time's up. I'm almost done. So we're just going to solve this equation. This kind of got blurred out. This is just the Korteweg, de Vries, I can't even pronounce it. This is with KdV equation. It's a nonlinear equation, and we can map it to the Koopman-von Neumann formalism. And here's what's beautiful. This is why it's a match made in heaven. For the photonic quantum computer, you can associate the U variable with a Q and the momentum variable with a P, which are now known as the amplitude and phase quadratures of a Q mode J. And they satisfy the same commutation relations. So, and this is on what is equivalent to an infinite dimensional Hilbert space. So just plugging into the KVN formula, you get these P's and Q's. This turns out to be a Gaussian term. This is a non-Gaussian term, and I'm almost done. And this is a lot, but this is basically just, we'll be sharing these slides, but Olivier spelled out exactly how he can implement the Gaussian part and the non-Gaussian part. We're going to apply this using the Trotter-Suzuki formula, doing P steps. And then at the end, what we're going to just do make measurements, and that's going to be the averages, just like I told you, we calculate expectations, and that's going to be the evolution of the equation. So we're going to solve it on a photonic quantum computer, and I want to thank Olivier and Jinfeng, and thank you.